Welcome. The first one is uploaded in the new series of using RStudio to do basic regression work. As I said, there's going to be more to come in the series, so look out for them. So there's two series currently that I'm working on. The one series is on general equilibrium using the Ep.2 box diagram. Apologies. And the one series is on setting up RStudio to do some basic regression work. So those are two series that I'm working with, and let's see how far it goes. Thanks for joining me. Thanks for supporting the channel. If you're not a member, please click that subscribe button. you won't be sad. You'll enjoy it. So with further ado, let's continue. So we ended off with creating our data time series, creating our data variable within our data set. Remember, I've got my data set, loaded in my project folder. I've installed some packages. I've activated the packages. I've added my data. I've checked my data, cross-correlated my data. All seems, if you look at here, all seems good, and I've created my date variable. Okay, I'm not going to go back into all the details of that. That's in the previous video. Okay, so remember what we have is we have all these names for my variables, and as I said in the previous video tutorial, it's already complicated because you've got long words and you've got a combination of capital letters, small letters, etc., which is not ideal. It's better, could be worse, but it's not ideal. So that's what I want to do, is to make it even less complex, make it even more straightforward. So I'm going to rename them. I could rename them in the data set. That's not an issue. But if I don't want to go for all that effort, I'm just going to rename them in my script. And there's how I rename it. So max is maximum temperature is renamed to max. Minimum temperatures are min. Temperature difference is temp. Wind speed W. Palmer P. Soil moisture S. Precipitation R. And then this date variable that I've created is simply just T. Now that's very, very nice and short and sweet. You shouldn't be able to stuff that one up. Well, I hope so. If you're me, then most probably you can. I can stuff up anything. But anyway, because if I have to continue writing, you can copy and paste it, but it just takes a lot of time and effort. So to be much more efficient, participation, I just use R. Soil, I can't forget it. I can't misspell it, etc., etc. So this is up to you. You don't have to do it. But if you're long, complicated names, my suggestion is do it and then just run it. And you see there it sits. Because it's all stuff that I've now created. It doesn't exist. It's been created. Now, if you don't want to do that, you can change it directly in your spreadsheet. That's totally up to you. But for me, I'll do it there. Now, there's our variables in our data set, nicely set up, nicely generated. No problems at all. We're all good to go. Okay, we're all good to go. Now, just for interest's sake, data conversions. So if I want to amend the data, if I want to change the data, if I want to, and there's a number of reasons why we do data conversions. For example, if I want to work in log formats, or if I want to work in first difference formats, whatever the case might be. This is how I would convert it. So if I want to convert a variable into log format, it's simply just the log, and that's just my name again. It's just log in brackets and the name of your variable. Now it's going to be the original, it's going to be the new one. It's going to be the original because that is the data. Okay. Max here doesn't have any data. It refers just to this one. Okay. So I can use that variable. If I want to lag something, so I want to lag the variable or just the original variable, I can just do -1 lag. So let's just say it's max temperatures, not the log one, the original one. Come on. I can just copy that. Let's say that's the original and lag it. And difference is just diff. So log is log, lag, and then the comma, how many periods you want to lag it. And then difference is just that one. So let's quickly run it. And you'll see they are there. There's the log one. There's the lag one. And there is the difference one. Okay. And we can, let's say we want to summarize it. So let's summarize it as lag. So there's the original one. There's the log one. There's the lag one. There's the difference. Let's look at the basic variables. So there's the summary, it's 16. There's the log one. There's the lag one, which should be exactly the same, except the n would be less. And the difference one. There's the difference one. Okay, so fairly straightforward, nothing to it. If you want to do it, you don't have to generate it like this and then add it in your equations. You can just use this in the equations. But if you declare it up front, you don't have to use this in your equation. You just use this because you've already declared it. So that's up to you how you want to do it. And I said, if you want to do the log, you can do the log, etc., etc. Remember, you can't do the log of the difference because of the minuses. However, you can take the difference of the logs. So you can play around with the variations on this. And that's just because a lot of times when we do regression, we like to work with the logs. And if you want to have a dynamic regression, you want to include the lags. And if you have a non-stationary, you want to include the differences. So the reason for this is several, but it's basically to transform your data. And the reason why you transform your data typically is because there is there's all sorts of things. Problems with your data, like variance issues. That's why you want to log them, or stationarity issues. That's why you want to take the first difference. So just have a look at that, please, and play around with it and see what the numbers is. You can, and again, you can do this in Excel as well. You don't have to do this in R. You can do this in Excel. So you can go to your original database, and you can just log all the variables here. I use lin, so you can log it, you can difference it, you can lag it. So you can do it in your database as well. But for instance, I've decided to do it here. Now, there's some pros and cons. In the database, you can exclude all the errors, and here you have to compensate if there's diffs and errors and things like this, but we'll get to that. Okay, so this is just data transformation techniques within RStudio. Okay, and then just a summary. Now, here's plots that you can do. This is a basic plot that you can generate. You see it there. So it's just plot T. Remember, we declared T as date, and we declared max as maximum temperatures. So you can put in the names as well there. So you can say plot date and max temp. You can do that as well. Let's see if that works. Nope. It's not, or max temp. You see the problem is it must be a capital. And we run it. You see it's the same thing. So let's just delete it. So you can just click on this clear plots rather should be clear. So you can see I can do it that way. Or I can do it that way. So it's exactly the same because I've declared these variables as that. So it works both ways. Okay. But you'll see now I can zoom out. I can make it bigger. I can zoom in. But you'll see this is, yeah, it's the raw data. Okay. It's the raw data. It's rawer. That's the right word. It's very, very raw. It's just the observations. Okay. But you'll see it's got the dates. And it's very, very, how do you say this? Random. There's no particular pattern in here. And you can see the variants are fairly constant. If you want to go that route, you see there's an upper band and there's a lower band. There's no significant outliers. So just looking at this, it already meets certain criteria. There's no significant outliers, meaning there's constant variance, and there's no specific trend. It looks fairly random. And that is to be expected given our significant data set. We have a huge data set. So the more data you have, the more likely your data is to become like this. Okay. And this is exactly what you want. You want your data to be random, without outliers, constant variance, all those sort of things, mean reverting, all of those sort of things. When that's the theory of econometrics, then those things become very, very important. Okay, so that's important to do. We can do a histogram. There's a histogram of it. This is just the wind that we're going to plot. Let's not worry about that now, but we can do that now for each and every one. You can do a separate script, or you can just amend the script. So here we do plot. Let's say plot wind. There's the wind speed plot, and you can do exactly the same histogram. Just copy and paste it. Histogram for wind speed. Let's look at wind speed. Okay, and we can do a histogram there, and there we go. Looks normally distributed. Yeah. Looks fairly normal. Let's have a look at temperatures. Temperatures doesn't look normally distributed at all. And that makes sense because, well, not really. That's maximum temperatures. Why is that looking like? Sorry, that's the participation. Rain. That, I must say, that doesn't look right. So there's our max temp. That looks again, well, it's got two peaks. A peak at the lower end and a peak at the higher end. So it's typical of seasonality. Typically when you have seasonal factors, because you've got winter and you've got summer, and you've got in between being spring and autumn. So it's important that you understand your variable, the characteristics of your data, and then these sort of figures makes a lot of sense. So spend some time getting to know your data. Then let's just clear that. Then if we want to add a number of graphs, we can do that. So basically partner, and this is the column row format. So one row, 3 columns, and the 3 variables that we want to plot. If I change that to 3 and 1, it will be 3 rows and 1 column. Let's quickly do that. See, 3 rows and 1 column. But these graphs, as I said, I prefer to do them in Excel. Because this is very basic graphs, nothing to it. I mean, if you present this, it's not going to look very professional. So I wouldn't. But the idea here again is not whether these graphs are nice or not. It's just basically to confirm that our data is okay. And again, we can compare it to if we do the graphs in Excel itself, we can just have a look at it. So this is just basic visual presentations of the data. Basic line of observation plot, basic histogram. You can learn some things of it, but again, as I said, it's not the end of the journey, it's the beginning of the journey. If we want to generate a little more interesting graphs, a little bit more relevant graphs that we can copy and paste into our report, where we're going to do a bit of more detailed analysis, we can generate time series charts of it. Okay, so first of all, we're going to generate a time series. So in this case, I call it max time series, TS, and then again, it's up to you. TS for time series. What are the variables that I want to create? I want to create a time series from max. What is max? I've defined max as maximum temperatures. Okay. Frequency is 12, meaning 12 months, monthly data, start date and end date. Very straightforward. Nothing to it. Just check it the format, your beginning time and your ending time. Okay. And I'm going to run it. See, nothing happens because all I've done is created the time series. There it is. I've created the time. You see, every time we create something, it sits here. Now I want to plot it. I want to plot this time series. So I'm going to plot the time series. What I'm going to plot? I'm going to plot my maximum temperatures. And I'm going to have a heading. The heading is called max temp. My X label, my X axis label is time. My Y axis label is degrees. My column color is red, and the line width of my column is 3. And I'm going to run it. Let's just quickly take that away. And I'm going to run it. And there it sits. You can change the color to whatever color. You see there's orange. You can change the, let's make it 6. We can change the width. Let's see the width. So we can change it. You have to find your own preferences. You can change the dates here. You can change it to 1980. Just rerun the whole thing again. See, 1980. So you can play around with everything that's in blue, and typically what's in curly brackets. Those are things that you can change. Okay, and you can do the same for all the others. So I'm just gonna basically run all of them. You'll see it will update it and. You don't have to, but it's up to you. Okay. So that's just adding the data, looking at the data, representing the data, transforming the data, all those sort of nice things. Those are all things that we've done now. So you'll see there's some code for some other things, but what I want to get to, we can do stationary, we can do that at a different time. I can do autocorrelation and partial autocorrelation maps. Let's have a look at that. We can do partial autocorrelation. And you can clearly see the seasonal patterns here. Anyway, that's not what I want to get to. We've done all of that stuff now. I'm happy with what we've done now. Okay. But remember, the series is about regression, specifically OLS. So let's quickly say the OLS. What does OLS stands for? It stands for ordinary least squares, linear regression. Ordinary least squares, meaning, remember, we want our errors to be as small as possible. Why? Because that means our model is as accurate as possible. So if your errors are small, it means you have a good model. It fits your data. So that's basically what we do. Remember, our model will not capture 100% of the actual variable. There will be an error, which is a difference between my estimate and my actual. So, for example, if we estimate rain, if the actual rain is 20 and our estimate is 18, then we have an error of 2. Now that's much better than if we have an estimate of 5, because then our error is 15. So which model would you prefer? A model that generates an error of 2 or a model that generates an error of 15? Answer should be fairly obvious. You will want to generate a model where the errors are as small as possible. Therefore, ordinary least square. Okay. So the whole point is you run various permutations of these coefficients until you get a model where the errors are as small as possible. Okay. And that's the whole idea of ordinary least squares. It's focusing on the error that you can. Now the error sounds bad, but it's not bad. It's just the difference between the actual and the estimate. Okay, so let's do our first regression. Okay, there's my first regression. So I'm just calling it LMS, linear model S. I don't know why I've used S. But anyway, let's use S. Equals LM, that's for linear modeling. Okay, that's the function. R, okay, in this case, my dependent variable is R. What is R? I have declared R as precipitation rain. So in this case, rain, the rain is my, or precipitation, the fancy word, is my dependent variable. Then you've got this little curly sign, and that sits there just below escape, or just next to 1 or above tab. So that's that little thingamajig sign there. Okay, so as I said, on your keyboard, look at the top left, just next to 1, just below escape, just above tab, you'll find it there. It sits there. Okay, so that's that little sign. And my independent variables are maximum temperatures and wind speed. Remember, I've declared max is maximum temperature, W as wind speed. So I'm saying that rain as my dependent variable can be explained by maximum temperatures and wind speed. Okay, so what is the theory? The theory is, as remember, we have winter rainfall. So we would expect our maximum temperatures to have an inverse relationship with rain. So as the temperatures increase, rain will decrease, because summer, high temperatures, least amount of rain. Winter, low temperatures, most amount of rain. So that, from observation, makes sense. If you look at your data, you'll see exactly the same thing. Okay? You'll see exactly the same thing in your data. That the highest rainfall is in the winter, the lowest rainfall is in the summer. And so if we have a winter rainfall, summer is the highest temperatures, etc. Then wind speed. And that's an interesting one, because the wind blows almost always here in the West Coast. There's very seldom times where the wind doesn't blow. Although the wind blows the least in winter compared to summer. So one would expect a negative relationship there as well. However, when it rains, it's normally associated with a lot of wind, because it brings the rain over the ocean. So wind is an interesting one. And so you can debate either way. You can debate it as should have an inverse relationship. You can debate it as having a positive relationship. We will have to look at the graphs and so forth to see which side of the fence you sit. But anyway, let's have a look. So it's always dependent variable plus explanatory variable plus explanatory variable. And then my data, where must I go and have a look? I must go and look at my data. Now you don't have to include this, because that's the only data set. If you have more than one data set declared, then I think then rather use it. I just do it as a matter of course, as a matter of insurance, just to say, use this data set. So let's run it. So I hope that makes sense. I'm not going to go into the theory of regression and. That is in RStudio how you generate a regression equation. And I'm going to press on. And you see it's blue. No, because all I've done is I've run regression. I haven't got the results of anything. I'm just running the regression. There you see it sits there. LMS, it's there. Okay. So now to get the results, I'm just going to click summary and then LMS. So I'm just going to get the summary, and there it is. And there it is. So call, there's my regression, there's the residuals, basic descriptive statistics on the residuals. Residuals also the error term. Remember, we don't specifically put in the error term here. We don't have in here plus the error term. We leave it out. But remember, in my function, when I generate the equation, when I write the equation in the modeling, I must put in the error term. Ne? But when we actually run it in RStudio, we exclude the error term. It automatically adds on the error term. We don't have to specify it. Okay? Because remember, yeah, I don't have that specific key here. We normally express the error term. We normally express the error term as my dependent variable is equal to alpha plus beta 1 x1 plus beta 2 x2 plus my error term in this case. So that's the full, because that captures the estimate, and this captures the difference between y and y hat, where y hat is this part. This part is y hat. Okay, so I hope that makes sense. Let me go back. Okay, so we don't include the error term, but automatically, obviously, calculates the error term. Okay, so let's have a look. My coefficients. Obviously, this is the important one. So there's my intercept. So that basically means, remember, rain is in millimeters. So if my maximum temperature are 0, my wind is 0, then the rain, we can expect rain of 103 millimeters. So if my maximum temperature is 0, doesn't mean there's no temperatures. It just means that we have 0 degrees. So that's, what is 0 degrees Celsius? It's neither warm, neither cold. It's 0. It's freezing point. I think freezing point 0. Yeah, it's freezing point. So when my temperatures are 0 and there's no wind, okay, and then we can expect rain of 103 millimeters. Now, this is the West Coast. We've never ever had 0 degrees. I think we can get, not in the day anyway. In the night, we could get down to about 5-6 degrees. But I don't think of any day at 12 o'clock midday, because that's normally when they take the temperatures of any day having a 0 degrees. But the model suggests, the equations of the regression suggest that if maximum temperatures are 0 and wind are 0, because remember that's what the constant is there. The constant is, put it in a graph, the constant is on that, remember that's y. So that's my x1 plus x2 sits on my x-axis. So if this is 0 and that's 0, we're on that point there. And so therefore this is now 103 rounded. So if my x and my y is 0, then my x1 and x2 is 0, then my y would be 103. And this is what we're saying here. If that is 0 and that is 0, rainfall will be 103. Here's my maximum temperatures. Okay. So my maximum temperatures has an inverse, as we speculated, and it's statistically significant. So my intercept is also statistically significant. So this is what these three little stars imply. Remember, there's my significant codes. And remember, I'm just not just looking at a star. Remember, we're looking at the t-value and the probability. Rule of thumb, t, remember we ignore the minus. It's absolute, must be bigger than 2 for 95%. And the p-values must be less than 0.05. Okay. Because remember, what's the hypothesis? The hypothesis is that that value, that coefficient is actually 0, as we said now. That's the null hypothesis. So remember, small p, reject the null hypothesis. If we reject the null hypothesis, per definition, we accept the alternative hypothesis that the value is not 0. The alternative doesn't say the value is minus 3.382. That's not what the alternative says. The alternative says that it's not 0. Okay? That's what the alternative says. It's not 0, and therefore it has a specific value. In this case, 3.382, but the alternative doesn't say that the coefficient is 3.382, minus 3.382. Just say it's not 0. Okay, so that's important because we're estimating it as minus 3.382, but it could be minus 4, it could actually be minus 5, it could actually be minus 2, or we know it's not 0. That's what this level of significance means. That's important to understand because there could be, that coefficient could be either overstated or understated, depending on various factors that we'll get to. So that's important to understand. We're not sure, we just know it's not 0. At this stage, we just know it's not 0. So in the absence of anything else, we assume that that value is actually correct. Wind. In this case, it's positive. Okay, and that's why I've said it could go either way. It could go either way. It could go either way. But in this case, it's suggested that it is 1. However, it's not statistically significant. It's got a t-value of less than 2, and it's got a p-value of bigger than 0.05. Remember, what's the null hypothesis? The null hypothesis is that these two actually are 0. Okay, so null hypothesis is actually that. So let's quickly add in here. Insert a. What's a null hypothesis? Where's my. The null hypothesis is that x1 is equal to 0. What is my alternative? My alternative is 1 is not 0. That's all we're saying. So in this case, we need a p-value of bigger than 0.05. In this case, we want a p-value smaller than 0.05. Okay. So you'll see and R is now nice enough to give us these little stars. So look for the stars, as they say. If you see the stars, it's statistically significant. You don't see the stars, it's not statistically significant at that specific levels indicated by the amount of stars. So 3 is our best option. And remember our hypothesis. The interpretation, the interpretation is very straightforward. It's inverse. If maximum temperatures increase by 1 degree, rain participation will decrease by 3.382 millimeters. Okay, because temperatures are in Celsius degrees and rain participation in millimeters. Wind speed, if wind speed increased by 1.042 meters per second, by 1 meter per second, rainfall participation will increase by 1 millimeter. So it's almost 1 to 1. Okay. So interpretation is important of my intercept, my max, and my. So in this case, let me save there. If we would draw this, we'll have there a y when x1 and x2 is 0, we'll have a 0 there of y. x1 will force it down and x2 will force it up. So if you combine this and giving the size of the two coefficients, because remember this coefficient is minus 3.38 and that coefficient is plus 1,042. So most probably it will look somewhere like this if we can do it in 3 dimensions. Somewhere it will have a negative slope if you combine the two, because the minus is much, the size of the minus is much higher than the sign of the positive, and so forth and so forth. Okay. So before we come, so that's, and then other important variables is obviously my adjusted R square. So in this case it's 0.48. What does that mean? It means that this model explains, or these two variables together explains 48% of the variance in my dependent variable. So these two variables together can only explain 48% of the variance, the changes in participation in the range, which is extremely low. Okay, ideally you want the value closer to 90 and 90 and above. So that indirectly suggests there's 52% unexplained. That's a lot. So that means there may be other variables that we need to include. The issue of omitted variables, unobserved variables that we need to include. Things that we need to include there that's currently not. And then the other thing is the F statistic. F statistic, p-value, have a look at the p-value. What is the F statistic? F statistic is, let me just quickly insert new slide. Okay. And the F statistic basically is the null hypothesis of the F statistic. The null hypothesis of the F statistic is that x1 plus x2 is equal to 0. Alternative, x1 plus x2 is not equal to 0. And again, here we want a p-value of bigger 0.05, and here we want a p-value of less than 0.05. So in our case, the p-value is very small, and therefore we accept the alternative hypothesis. The alternative is that these two things together is not 0. What does that mean? It means that together these variables are statistically significant. Although wind speed is not statistically significant, but together they are statistically significant. Okay? Although they only account for only 48% of the variance in the dependent variable. Now again, we're not using the multiple square, we're using the adjusted R square, because the adjusted R square, as what it says, is adjusted for the degrees of freedom. So as you add more variables, independent variables, your degrees of freedom increases, and therefore this is adjusted for that. So for example, if I just add variables, my multiple square would automatically just increase. Where that's not the case for the adjusted R square. The adjusted R square, okay, you can see it's less, okay, accounts for degrees of freedom. So that's the basic. There's a lot of things that's not included in here, that needs to be included in here. But for now, that's the basic output in RStudio. Now you could do exactly the same in Excel, and it should give you exactly the same information. But that's how far you can go into Excel. So up to everything that we've done now, we can do in Excel. Okay. But if we want to go a little bit further, dig further into the regression, then Excel is not your friend. RStudio becomes your friend. And therefore I suggest you rather start from the beginning working in RStudio. Then you can cross correlate, you can all these things in Excel, but I would just do everything in RStudio. So that's the basics. So we're going to continue working on this now because we have a basic model. There's good things and there's bad things about the basic model. The good thing is we have some indication of variables that work, that's meaning work, let me not push it, that should be included, that are relevant, and some that's not relevant. We know that the model itself is woefully underestimating the estimate, meaning we've got a large error term indicated by this, etc. So there's some good stuff. It's a beginning. Let's call it a base equation. And that's normally how we start. We generate a base equation, and then the fun and games start. In that becomes a trial and error process. We add, we subtract, we check, we add, we subtract, we check, etc., etc., etc. So we'll continue with that. Okay, we will continue with this in our next video, working on this. Okay, so that's basically the two command lines that we're working with. Okay, just see how they are expressed. Now we can, as it expand on this. There's a whole lot of things we can work for this as we go along. Okay, so the first command line just generates the equation or the regression. The second one displays the results of that specific regression. And then it becomes, as we discussed, or as any textbook will tell you, now it becomes a matter of analyze and interpret. Analyze and interpret. Analyze and interpret. Okay, and that's the way we're going to continue with it. So with that said, let's park there for now. I don't want to start something new because there's a whole lot of tests that we're going to perform and so forth and so forth. So let's just park there for now. I think that's more than enough for this particular video to get you guys going with a basic regression model, regression equation within Excel. But remember, your groundwork needs to be in place. If your groundwork is not in place, then you're going to get here, you're going to get rubbish. So that's why we spend all that time and effort on making sure our data, our transformations, our declarations, all those things are in place just to get to this point. But you do those things up front, once off, and then it becomes fairly straightforward going forward. Okay, so let's park there for now. Let's say thank you for listening and thank you for watching. Welcome to engage with me if you have specific questions or you have problems. I'm happy to help you, to assist you. And then stay tuned. The next one is around the corner. Please, before you go, like, subscribe, share the video. It does mean a lot. It does help a lot. So with that said, I'll see you on the other side.